Okay, this is just going to be a very quick video going over the idea of exponentials. What are they? How do we use them? Where does the e come from? So, first of all, what do you mean by the term exponentials? Well, the word exponential, outside of a mathematical context, means something that starts off increasing very slowly and then gets faster and faster and faster much more quickly. So it's essentially a shape that looks like this. And in maths, anything that plots a graph that looks like this is an exponential function. The most common types of these are y equals anything to the x. So y equals 2 to the x, or y equals 3 to the x, or 4 to the x, or 147 to the x. These are all exponential functions. Don't get them confused with things like x squared. These are not exponential functions. They might look like half of one. If I kept going this way, that would kind of be an x squared graph, but they are completely different. An exponential graph must have x in the indice, or in the exponents. The reason for that, if we think about it kind of logically, is if I just do my powers of 2, so if I just stick to this graph, y equals 2 to the x, well, my x values are going to go up nice and linearly. 1, 2, 3, 4, 5, 6, etc. But my y coordinates, well, it's going to start off with 2, then it's going to go 4, and then 8, and then 16, 32, 64, 128, so on and so on. It gets bigger and bigger every time. So even though my x values are increasing slowly, just by 1 each time, my y values are increasing much faster. Starting off at, I suppose here would be a 1, and then I'm going to a 2, and then to a 4, then to an 8, 16, 32, 64, and it ends up looking something like this. Now, these graphs are very, very commonplace in everyday life, in most science, which is why we are so interested in using them. One of the most recent examples is during COVID. These were all the range, because unfortunately a lot of the graphs of cases and hospitalizations and things look like this. So during COVID, watching the briefings, watching things like that, there were a lot of graphs that looked like this. And unfortunately, in a lot of medical settings, even in physics settings as well, graphs look like this. So it's important we know what they are and how to deal with them. So now what I want to talk about is this concept of this letter E. So for the first time on this channel, but I'm sure it won't be the last, we're going to encounter this guy here called Leonhard Euler. Not Euler, it is pronounced Euler. And he was a mathematician, and he basically did everything. There's almost a running joke in maths and in other sciences as well, that if it was mathsy, he did it. You've got Euler's number, Euler's constant, Euler's equations, you've got all sorts. We even started having to name things after the second person that discovered things, because too many things were called Euler. But one of his things is Euler's number, which is this guy here, E, and it relates to this idea of exponentials. Now, to kind of show you where we get this idea of E from, we're going to need to use a little bit of calculus, a little bit of differentiation. If you haven't covered that yet, even though you probably should have before looking at this kind of thing, that's fine, but we are just going to be discussing this idea of gradients. So what I'm going to do is I'm going to sketch a graph of roughly 2 to the x. Now, the first thing that I want to notice here is that if I continued this graph forever, my 2 to the x graph will make an asymptote with with y equals 0. The reason for that is there is no number that we can put into 2 to the x to make 0. And this is true for every exponent with an x in it. 3 to the x equaling 0, 4 to the x, 147 to the x. we will never be able to find a value of x that 2 to the power of that is equal to 0. I mean, you might think, well, 0, but 2 to the power of 0 is 1. Anything to the power of 0 is 1. And any other number you throw in isn't going to give you 0, which means we are never going to be hitting at 0. The next thing I want to note is that all of these graphs will be hitting the y-axis at 1. This coordinate here will always be 0, 1. For a similar reason, no matter what the function is, any number to the power of x0, because here x is 0, any number to the power of 0 is equal to 1. Doesn't matter what that number is. So we're always going to be crossing the y-axis at 0, 1. Anyway, that's a little bit beside the point. To get this idea of Euler, I have drawn this 2 to the x graph. Now, because exponential graphs change so quickly, they have an interesting property with their gradient, which is that if I draw my a graph of the gradient of this graph, okay, let me try that again. If you notice loads of cuts when I'm drawing graphs, it's because I, quite frankly, suck at drawing graphs, and the last one looked unacceptable, we'll say. So, if I want to draw the gradient of this graph, it looks something like this. Much better, actually, a smooth line. So this is my gradient, dy by dx of 2 to the x. And what you'll notice is that because of how this graph is structured, because it changes so rapidly, the gradient, when plotted on its own graph, has the same shape. It's not exactly lined up, but it has its own shape. And in this case, for 2 to the x, the gradient function is slightly below my 2 to the x line. Yeah? If I plotted these, you can throw it into Desmos onto a calculator. If I plotted these, then I will notice that this dy dx graph is the same shape, just slightly lower. Now I'm going to quickly switch to a y equals 3 to the x graph and draw the gradient function for this as well. And again, if I do this, I notice it looks like this. Again, it's the same shape. That is a common feature of these exponential graphs, but this time it is slightly above. So with the y to the 2x line, it was slightly below the gradient function. The gradient function was slightly below the line, but with y to the 3x, it was slightly above. So the question is there a number somewhere between 2 and 3 that if I raise that number to the power of x, my gradient and my standard function lie on top of each other? The answer, you may have guessed, is yes. And this is what Euler's number is. It is approximately 2.7. I'll just leave it at that. It goes on for ages. It's like pi. It is an irrational number. It goes on forever, but we can just leave it as 2.7 for now. Now, what this means is, if I take Euler's number, and exactly Euler's number, and I raise it to the power of x, so I might just, I will keep this line because if I have to draw another one of these, I might scream. So this blue line here is going to be e to the x. I'm not going to put 2.7 because that's not precise enough. I want to use e. And then if I were to go through the long and arduous calculations to find the gradient of this, I would notice that it is exactly the same, and it will lie directly on top of it. So this is a very, very important property. It's also kind of a cool property, that the function e to the x is not able to be differentiated. Or, that's technically speaking out of tune, it is able to be differentiated, but it just loops back and turns into itself. The derivative of e to the x is equal to e to the x, which incidentally is also equal to the integral of the e to the x. It all just loops back on itself, and this is just a nice little quality within e, and it's also a nice little number to use in mathematics.